Good morning, everybody, and welcome back to the machine learning course. So yesterday, we wrapped up the discussions about neural networks and looked at the link between the automatic differentiation, or normally something which is implemented via software like JAX or AutoGrad, and the backpropagation algorithm. And then we started looking at the differential equations. Now, just to remind you quickly, the video from yesterday is something you will find down. If you just scroll down on the README side file here, you will find the video from yesterday, and you will also find the handwritten notes. So the topic which we will continue with today is about the solution of differential equations with neural networks. And this is a very interesting topic. And there's a lot of research being dedicated to the usage of differential equations. So I'm going to repeat some of the things which we went through yesterday. And when we are done with that, we are going to switch over to our final topic, which will be about convolutional neural networks and recurrent neural networks. And these are topics which we will also discuss next Monday. Then, after the winter break, in the middle of January, roughly, we will also have sessions where we try to wrap up what we've gone through and discuss the final project. And eventually, we will also discuss the final deadline, which typically is something which we have set for, let's say, the middle of February or towards the end of February, so that we can produce the final grades in due time. So the material which you have access to is the one from day 8, or session 8 as we called it, and session 7. And if you go to the address which we have up here, if you click on this link here on Confus, this link gives you the daily or the weekly material. So if we scroll down, you will find then the one on session 7 and session 8. So I have to change this title, but it's session 8 and session 7, which are those which contain the discussion of differential equations. So I haven't updated the titles yet here. But the session 7 is the one about convolutional neural networks now and recurrence, and session 8 is the one about differential equations. So you also have access to the Jupyter notebooks. So the Jupyter notebooks for differential equations is the one which I will use now. However, what I wanted to do before we move on to look at the specific examples, I just wanted to remind you a little bit about the basic mathematics which is used in solving differential equations. Now, for the final project, if you are interested, we can also have a path which deals with the solution of differential equations with deep learning methods. So what I want to do now is just to switch back to the whiteboard and go through some of the basic mathematics for solving differential equations with neural networks. So let's quickly switch to the whiteboard. Now, if you look at a differential equation, you would typically have an equation of the following type. So we have suppose we have a specific function, a d, and then we have a function which we just call g here. Or maybe let's just call it gd of x. And this could now be given by some specific function, which we now could call h of x, like this. Or we could simply just write it as a g prime of x. And typically the way we would now solve this type of equations is to rewrite it in terms of a new function minus this g of x, which is equal to 0. So this function g prime of x is something which is known. It's given by a specific function, h of x, or g prime of x. And then what we want to do now is actually to drive this to 0. We could have higher derivatives as well. this is one of the simplest possible differential equations we can think of. So in essence, if we want to generalize this, we can write this in terms of a specific function. So where f of x now is defined by this function here. But in general, what we would have would be a function which depends on x. It depends on, so we have this g of x here. It depends on the derivative of g of x. It depends on the second derivative, and it can depend on higher derivatives. And in principle, this is equal to 0. Now, what we could do when we now solve this in terms of neural networks, but this is also a kind of recipe which is used in other types of differential equation solvers, which are called iterative solvers, is that we could attempt a guess on the function g of x, which we want to find. And the guess could be something like a trial function, gt of x, which is now given by some function h1 of x, plus a new function h2, which is a function of x, but then it's also a function of a neural network, which depends on x, the input values, and the unknown parameters theta. So theta are the parameters of a neural network. So this n of x of theta is a neural network now. And this neural network takes as input the variables x. So you can think of x as the input nodes or the input layer to a neural network. And then this neural network gives an output, which is this n of x of theta. And then theta are then the parameters which we need to optimize in the neural network. So that means that what we would have then is that x is the input to this n of x of theta. And then we have theta are the network parameters. And depending on how many layers we have, so theta would then be this collective container for the weights in the first layer, the bias in the first layer, and then this goes on depending on how many layers we have, all the way up to the final layer, which we labeled with an uppercase letter L, which is the output layer. And then through the optimization of a cost function, we would then be able to set up an optimization problem. And the typical cost function would be something like C, which depends on X, and these parameters theta, which are the parameters we want to optimize. And a typical one, which we have encountered before, could be something which is close to the mean squared error. But what we would have then would be a sum over I equal 1 up to n, and where we are simply requiring that this function f, which we have set up, which depends on x, and g of x, the unknown function, and g derivative of x, etc. And then we would simply square this function. So that means that if we go back to the simple example we looked at the beginning here, so this simple example which we have here, then what we will do now is simply to replace this with a g of t. This function here is a known function. So a typical differential equation which you have encountered many, many times is the following. So let's look at a very, very typical example before we move on. So the example function is a famous differential equation where we have the derivative of the function g, which is simply given by some constant minus gamma times g of x. And we know the solution to this function when we integrate it up. That one is just given by some constant g0 times the exponential of minus gamma times x. Gamma is just a constant. So this is a constant in front of the function g of x. This is the simplest possible case which we can actually think of. So this type of equation then is an equation which we now could plug in into that differential equation, which we have here, and simply rewrite it by shifting the known expression which we have to the left. And then we have this function here, and then we square this function so that we actually emphasize the large differences, which would be the same as we saw previously when we looked at the mean squared error. In essence, what you're seeing here is the basic step which you would have in solving a ordinary differential equation, but also when you're solving a partial differential equation. The only thing which would change then would be the way we actually make the ansatz. So this ansatz, which you see here now, is a function which we want to obey the initial conditions. And if we go back to this simple example, we know that this g0, which we put here, this is simply the value at the g of x equals 0. And when we want to compare this with the standard numerical methods, we could compare this with this type of Runge-Kutta solvers. We could even take the simplest possible method, which is Euler's forward stepping method. And if we now just remind ourselves a little bit about what we did yesterday, when we solve this type of differential equations, we actually need to discretize the equations. But let's, before we do that, let's look at a possible trial function, which then will include these boundary conditions, which we have here, and then go back to this form here and see how we could actually parameterize it. So let's look at a way to set up the trial function for this specific case. So the trial function, which is the one we start the neural network with. So this could be something which we have a gt of x, t stands for trial. So we want now to write this as an h1 of x plus a function h2, which now depends on x, but also on the neural network here. So this is an n of x, and then we have the parameters theta. So one possible way to set this function here is in the following. So we could now have some parameter gamma, which we put equal to 2 here, and then we could have a parameter g0, the initial condition, which we just put equal to 10. So if we then go down to the way we could set up the trial function, we could now put this gt of x, which is equal to g0 times x, plus x times the neural network times x, and x is the input variable, and with theta here. So that could be a typical way by which we could set up the initial conditions, or respect the initial conditions, and then simply have a function then, which now contains these different initial conditions which we actually want to respect here. So we, with that kind of initial trial function, we have then a function which we can then use to set up the initial values, and then we can move on and simply just set up the solution of the differential equation by setting up a neural network. So we can then compare this with the standard differential equation solvers. So we can compare. Sorry, I actually had there is a small error here. So this times x is not there. So this should just be g0 plus x times n. So when x is equal to 0, then we are just left with g0. And then x being 0, when it multiplies the neural network, it gives us 0. So this is a typical trial function which we can set up. And then we can compare with, in this specific case, with analytical solutions, which is pretty easy to obtain. And standard numerically ordinary differential equation solvers and standard ODE solvers. So the way we are going to solve the equations here is actually to look at the specific domain of the variables. So we could now simply define that x is an element between 0 and 1. That could be a typical domain for which we want to solve this equation, just to give you an example. And then we would typically discretize x. So x goes over to x of I, and that is given by some x0, which is the first value, plus some I times a step size, delta x. And this I goes from 0, 1, 2, up to a final number of integration points. So we have n plus 1 integration points. They are also normally called mesh points or grid points in the literature. Then with this discretization, what we will have then is that delta of x will typically be defined in terms of the last point and the first point divided by n. And it's pretty common to solve with x0 equal to 0. That's a possible starting value. And we have the boundary conditions. So we would also discretize the function g of x. That becomes a discretized function of x of I. And we will typically write it as a g of I. And yesterday we derived Euler's forward method. And in that specific case, what we have is that the derivative of g, so g of I, which is the derivative of g at x with x equal to x of I, is then given by g of I plus 1 minus g of I, and we should put an approximation sign here, divided by delta x. And this g of I plus minus 1 is the same as the function evaluated at x of I plus minus delta x. So these are just shorthand notations. And that means that we can then integrate up g of I plus 1, which is then equal to g of I plus this delta of x times the derivative at the same point, x of I. This is called Euler's method, and it's the simplest, or Euler's forward stepping method or forward integration methods. So this is Euler's forward or the explicit method. These are different names which are being used for this type of algorithm. And it's called the forward method because we are just stepping forward in time or in x, depending on the integration variable we have. It's called the explicit scheme because the next point is explicitly defined in terms of the previous points, where we start the integration at the x0, which means that everything is known at x0 because g of I at x0 is a known quantity. And we assume also that the derivative is known at x0, and that means that we can start integrating up. Now we have many other methods. We have the modified Euler-Kromer method. We have the family of Runge-Kutta methods. There's a plethora of different numerical methods for solving differential equations. And you most likely you have met quite many of them in your studies. Now, what we will do next is simply to optimize our neural network then is defined by the optimization of the parameters theta. These theta hat are the optimal parameters. So we will typically minimize this difference between the left-hand side and the right-hand side of the differential equation. So we would have a minimization over the values of theta, and then we have this cost function, which is x, and depending on the parameters theta, which in our case is equal to the minimization of this function 1 over n, and in many cases people actually skip the 1 over n term, and then we have this function f squared. So this is typically the function which we would now minimize in the neural network. So let's take a look at the Jupyter Notebook now and see if we can actually get something which makes sense and which is perhaps even better than the standard numerical method which we have encountered earlier. So keep in mind also that in the implementation of a neural network, we are also going to discretize the number of integration points, which means simply that this solution here, the minimization, is done with respect to a chosen set of values x. So the values x which we could have 10 points between 0 and 1, we could have 100 points, etc., etc. And then we would simply use these as input variables, and every x spits out an output, which in our case, when we put in an x here, we obviously spit out an output. So let's see if we can solve this type of equation, and we go back to the Jupyter notebooks. So let's take a look at those. And if you have any questions, please feel free to unmute yourself and just ask questions, or just put them in the chat if you prefer that. So let's look at the first examples here. By the way, there are also some textbooks which I wanted to mention, which are actually pretty good. And you can look up this textbook by Yadav and Kumar. You can actually download it for free. It's a Springer textbook, and it contains much of the same things which you will find in the slides here. Many of these slides were actually developed originally by Christina, which is now a PhD student in computer science at the University of Oslo, and she's actually working on these topics. So what you will see first here is actually basically what we discussed now, and this is the example which we are going to look at. And the differential equation, as we saw, has a simple analytical solution, so it's easy to compare with. And the ansatz which we are setting up is actually this ansatz here. So this is a trial solution which we set up in our first attempt at a neural network. So when we are now propagating forward, doing the first feed forward propagation, this is the ansatz for the trial wave function which we have. And then the neural network will just be set to the parameters for theta, or which we have written as p here, where these are the weights and the biases of a neural network. And then we would simply then repeat this after a number of iterations and see what we get. So that means that when we are performing the calculations now, what we are optimizing is the ansatz for the derivative minus the ansatz for the solution which we have. And the not the solution, but actually this is the ansatz for the right-hand side of the differential equation, because the right-hand side of the differential equation is given by this term here. So for every iteration in a neural network, we have a trial derivative and we have a trial function here. So that means that we need to take the derivative of the wave function as well, in addition to taking the derivative of the cost function, which is now the square difference between these two quantities. Any questions so far? Does this sound okay? Okay, so let's now look at the implementation of neural networks. So I'm not going to repeat that, because this is something which we discussed earlier. And in this specific case, we are going to use the sigmoid function as an activation function. We can obviously change that to more advanced activation functions. And these are the same setups which we discussed earlier, and we repeated some of them yesterday when we discussed the general layout of a neural network. And in the first example here, I'm going to use a standard sigmoid function, as I said, and this is just the neural network with one hidden layer. So if we run this, you will first see that the trial difference between the derivative and the trial function is actually pretty large. So this is our original cost function. And in our case, we're just taking 10 integration points. So if you now look at the integration points which we're dealing with, that's set to 10. So we are setting the x values between 0 and 1. So this is the input of a neural network. And we are performing 10,000 iterations. And we also put the hyperparameter lambda to 0.01. And then you see also that the neural network now is going to contain a trial function. And then we also have the analytical result here, which we can compare with. And you can see now that after this number of iterations, and with a hyperparameter lambda, 10 to the minus 3, we're actually getting a result which has a absolute difference between the exact value and the numerical one which we get from a neural network, which is actually pretty decent. It's not optimal, but we can compare this with a standard differential equation method like Euler's method, which is actually not the best method. So we can now specify this one also to have with a specified number of hidden layers. And we would typically have just one input layer and one output layer. And we can make this more general, so we can actually have more hidden layers if we want to. So we could then just rerun this with 2 hidden layers and just see what happens. And this is something which then we can also compare with analytical solutions, which you will see down here. And we are going to look at some other examples as well. It takes more time because we are performing 10,000 feed-forward steps and 10,000 back propagation steps. And we have the same values for the hyperparameter lambda. But now we're having a network which is a little bit deeper. So you can play around with this as we did before. But as you can see here now, this takes a little bit more time to run these calculations. Now, another example, and you can see now that the value when we added another hidden layer doesn't actually improve. It's actually getting a little bit worse. So we have a final cost which is actually increased. So it means that with just one hidden layer here, we were getting a result which was pretty decent. Now, let's look at an example with population growth. So a so-called logistic model of population growth. That assumes that we have a population which converges towards an equilibrium population. And this is normally modeled with an equation which is actually not that different from the one which we had before, except that we have a g of t here times a g of t. And then this is multiplied with a constant here. And the model is now given by this equation here. We fix a g0, we fix the parameter alpha to 2, a equal to 1, and we put g0 equal to 1.2. And then we would again use a similar trial solution here. So we would have a g0, and when we have t, so when t is equal to 0, then we would simply have, so in this case I have time instead of position. But it doesn't matter what we call this variable. We could actually solve this equation with x as well. It doesn't matter, but now we want to interpret t as time, since we want to look at the time evolution of the population. And this equation also has an analytical solution, which we can easily set up. Here I've been using AutoGrad to calculate the derivatives. So we can now run this in much the same way as before. So if we now set up the function, in this specific case, I actually have an ansatz, which is a little bit better. And you see now that the difference between the analytical solution and the neural network solution is actually pretty close here. So this is actually a type of problem for these 10 integration points where we are getting pretty close. This may not be the case for all the types of equations. Now, the next thing which we could do now, simply to compare this with Euler's method. Now, you might say that this is a little bit unfair because Euler's method is not actually the very best method to use, but it serves now just as a simple approximation in order for us to compare the results of our numerical calculations with a neural network. So in this case, we are simply just implementing what we discussed before. And then we have a stepping here with a t of I, which is equal by I times delta t. And then we have this update rule, which we have here. And then we can plug in Euler's method, where we simply have a stepping in terms of the previous stage plus a delta t here. And this is basically the implementation of Euler's method for this specific case. And where we now also have a g0, which is the same as g evaluated t0, where we typically put t0 to 0. And this function again is now, as you can see here, we are setting up the values of t which then run from 0 to 1 again, and we have only 10 points. So in a certain sense, this is a little bit unfair to Euler's method. And I'm performing 1,000 iterations, and I also have a hyperparameter lambda, which is put to 10 to the minus 3. And I have my ordinary differential equation solver network, which is the same as before. And then I have my trial function, and then I have the analytical solution here. And then this contains both the solution to Euler's method, which is extremely simple. So this is G Euler, it's the Euler method solution. This has an initial value, which is given by G0. And this is the simple implementation of Euler's method. So you might say, I mean, why should I do a neural network when often Euler's method or modifications of this, let's say through the family of Runge-Kutta method, is actually so easy to implement here. But let's see what we get then. So we are rerunning with the same neural network. The initial cost is pretty small already. And then when we now do the analysis in terms of the solution of the method with Euler's method, you see now that Euler's method is actually a method which doesn't compare that well with 10 integration points. And you see now that the max absolute difference between the exact analytical solution and the neural network solution is actually pretty small with only 10 points, whereas Euler's method is actually 1 order magnitude larger in its error. And that means that when we now are using Euler's method, we see clearly that, and compare that with a neural network, we see that this is a case where a neural network actually beats Euler's method. However, if you're making a comparison between the number of floating point operations you need, you would then see that Euler's method is by far superior. It's extremely easy to set up. And in this specific case, although the neural network is actually beating Euler's method with a precision which is 1 order of magnitude better, then we are actually spending many more floating point operations. So you always have to make a comparison between the trade-off between the number of floating point operations you're willing to invest and spend and the precision which you want to achieve. Now, if we were to change this to, let's say, 100 points, then Euler's method would normally actually perform better. And then what you will see then is that this code is actually going to run much slower because the neural network will take much more time to train. So Euler's method will produce results basically immediately. And then the network will actually take a little bit more time. Now, what you see now is that the neural network has roughly the same type of error, but with more integration points, since we are making delta x smaller, or delta t in our case. So if you go back to Euler's method, when I now increase the number of integration points, that means that delta t is getting smaller, and it's getting closer and closer to 0, which means in turn that we are getting a better and better approximation to the derivatives. And you see now that Euler's method actually beats in precision the result from the neural network. So when I increase the number of points, the complexity of my neural network doesn't give a better result from the previous case, which was 0.04. And now we have, actually here we have 1 order magnitude better result, or even more, for Euler's method. So if we were to increase this to 1,000 points, you will see that this error becomes even smaller. So this is a case where we clearly see that standard differential equation solvers like Euler's method or the family of Runge-Kutta method actually do a much better job. So when I just used 10 points, the comparison was a little bit unfair because a neural network produces typically with just 1 layer. It will then produce a result which is tailored to that specific network with that specific number of hidden nodes. Any questions so far before we move on? But you see how easily we can implement the calculation of a neural network and use that to solve differential equations. So the basic idea is that you take the difference between the left-hand side and the right-hand side, and you want to drive this difference to 0. by calculating the gradients over and over again. Okay. So let's now look at the other examples here. Now, there is an equation, a famous equation, which can also be solved in this specific case analytically, depending on the function f of x, which we have here. So we have a second derivative, g of x. This is a problem which is not an initial value problem, but it is actually a boundary value problem. And one typical equation which you may have met when you took a course in quantum mechanics or quantum physics would be that of a particle in an infinite potential well. Or this could be the equation for a beam or a spring, which is fastened in both ends. And then you don't allow it to move, because then you have a boundary condition here where you put at the two ends, you put the result equal to 0. So this is not an initial value problem, but it is a boundary value problem. And in this case, we are setting x to be an element between 0 and 1 again. And then we fix the values at the boundaries. And we want to solve the differential equation for the values between 0 and 1, because we have fixed the values at 0 and 1. In this case, we are going to look at an example where this function f of x is equal to this function. And this is actually a case where we have an analytical solution which is given by this function here. Now, if you now look at the case here, I'm actually making a new trial function which is able to accommodate the boundary conditions. You see now that if I put x equal to 0, then g of 0 is equal 0. And if I put x equal to 1, then you see also that I have 1 minus 1 times 1, which is also 0, and multiplied with the neural network. So this is a simple way to implement the boundary conditions. In this case, we don't have an initial value. Just remember that. So this is a 2-point boundary value problem. Now, when I now want to solve the problem, I'm still using the sigmoid function. I'm setting up my neural network. I have the input layer, and then I have a hidden layer. And this is just now me setting up the different parameters. And keep in mind that since this is a type of regression problem, the output layer just produces the output or the input to the final layer. And when we now solve the differential equations, if we just scroll down here, I define my cost function, which is now defined. So I take the trial function. I have the derivative of the trial function, and I'm using automatic differentiation to take the derivative of this function. So this makes it much easier to calculate derivatives for different types of problems. So I can actually, with a given trial function, I then have, with automatic differentiation, it's very easy to actually set up this as a generic solver. And then what I want to optimize is the difference between the left-hand side and the right-hand side of the equation. So this is my error, which I then want to optimize. So this is my cost function, and this returns actually the cost function, this specific function which you see here. And then I have my trial function, which is now simply given by my neural network multiplied with this ansatz here, which respects the boundary conditions. And then I have the analytical solution. And now I'm solving this again for 10 points. And I have the number of hidden neurons. I have 2 layers, 200 and 100. And I have the number of iterations to 1,000. And I have a hyperparameter lambda. Now, what you will see here is that I'm not tuning the learning rate. So I'm not setting up the gradient descent method in the most efficient way. But this is just very schematic and a simple function. And then I calculate the differences. You see that my initial cost function is actually pretty large. And you will see also that this layer here gives actually pretty good results at the end. So the final cost function is actually 10 to the minus 3 times 3. And the max absolute difference between the analytical solution is actually pretty small. So you could say now that this neural network without any kind of knowledge about the wave function or the solution or the function we want to find, except for the boundary conditions and the differential equation we want to solve, gives actually an amazing result. So you can see now that when I plot it for these 10 points, the difference between the analytical one and the neural network is actually very, very small. I can compare this to a standard numerical scheme. So this is a numerical scheme then, where we now have the second derivative. I'm using a 3-point formula. So this is the equation which you see here, divided by this delta x. This is one of these famous expressions for the approximation of the second derivative. And this runs with an error term, which in this case goes like this delta x squared. So that's the step size which we have chosen. So this, the first arrow scales now like some high order derivatives. It's actually a fourth order derivative multiplied with delta x squared. So if delta x squared is delta x is small, then the results which we leave out are hopefully small. And then we can approximate the first derivative with this function here. And which you see is given by this one, which is a pretty standard formula in numerical solution of differential equations. You will actually be surprised to see that this is one of the standard equations which is used in solutions of differential equations. And then what we end up with is an equation where we have the second derivative, which is given by this equation. And then we know that the analytical function f of x, so this is a known function, is just given by this expression which you see here. And then we can multiply away this delta x squared. Then we take the discretized version of f of x, and then we have simply delta x squared times f of x of I. And then we have this equation here, which we then for every I can rewrite in terms of a matrix times the unknown function, which is given by this vector. And we are now not solving this for the boundaries, because the boundaries are known. And that's why we don't have g0 here, and we don't have gnx minus 1, which is the last point we have. So we need only because the boundary values are already set, and then g has to be 0 at the boundaries. And this is simply now something which we could rewrite in terms of a function here, where we have this f and multiply with delta x, and this would actually be an f tilde here, where g is the unknown function, a is a matrix which is known, and f is a vector which is known. So this is the typical way you would solve it. You would not solve this by matrix inversion, but you can actually use what's called a lower and upper decomposition algorithm, which for this specific case, which is a tridiagonal matrix with a constant along the diagonal and a constant along the two non-diagonal parts, then this is something which can be solved by an algorithm which is called Thomas algorithm. So we can repeat the same exercise before we now take a small break, and then simply look at how Euler's method, no, not Euler's method, how the neural network compares with the solution, the numerical solution, with a 2-point boundary value problem. And you see now that the absolute difference between the analytical solution and the neural network using autograd is actually pretty small. And with 10 integration points only, and again, I should state that this is a little bit unfair with the numerical scheme here, we are getting a result which is actually 1 order of magnitude worse than the neural network gives us. And you can see now the comparison between the different schemes for only 10 integration points. If I were to change this and have 100 integration points, then you will see again that the numerical error we make with the standard implementation of the scheme here with the what's called Thomas algorithm, then we will get a much better result here, because then delta x will be much smaller. So we can actually implement that by simply defining the number of integration points to be 100 instead of 10. And then you would typically see that the neural network would behave worse than the numerical differential equation solver, which is pretty standard. So that method which you saw now is actually a pretty standard method for solving this type of differential equations. So after the break, we're just going to look at some examples of solving partial differential equations. The reason why this is taking more time is simply that the neural network has to work much more, because we have 100 input values. And you see now that the neural network is also giving a pretty good result. So this is at the order of 10 to the minus fourth, this result here. But you see that the numerical scheme now gives a much better result. And we have a result which is essentially almost overlapping the analytical result here. And the curve is also much less choppy because we have now many more integration points. In the first case, we had only 10 integration points, but now we're having something like 100 integration points between 0 and 1. But you see that the results are actually pretty good, both for the neural network, where we simply have an ansatz for the function, and the standard numerical equation solver for this 2-point boundary value problem. Now, what you can say when you're looking at low-dimensional problems is that the neural network will never be able to beat these, well-established numerical solvers. The numerical network, the neural network actually has its strength when the dimensionality starts growing, because many of these standard methods, they actually rely normally on different matrix and linear algebra solvers. And these are obviously, they reach their limitations when the dimensionality grows. And that's where neural network would typically be superior to the solution of the differential equations using standard differential equation methods. So we're going to take a small break, if that is okay. And then we look at the solution of partial differential equations. And after that, we're going to move over to the next topic, which will be convolutional neural networks. And that will keep us busy next Monday as well. So what we looked at before the break was the solution of a standard ordinary differential equation. And in our specific case, this was a first-order differential equation. And then we looked at the type of problems which we can get when we have either an initial value problem, where we have some specific initial value, and then we integrate up, or whether we have a 2-point boundary value. And just to summarize a little bit what we saw, if we used few integration points, then a neural network would typically be superior to a standard differential equation solver. Now, the standard differential equation solvers represent different mathematical approximations to the derivatives. And these are mathematical approximations to the derivatives. They are normally functions which depend on the step size, delta x or delta t, times some higher order derivatives. And if we make the step size smaller and smaller, what happens then, which means also that we have more integration points, then what happens is that the standard numerical schemes tend to give better results than a neural network. So in this specific case, we actually train the neural network with 100 input values, and then we compare that with a standard numerical solver for 2-point boundary value problem, which is then solved by a standard linear algebra algorithm, which is called Thomas algorithm, and where we ended up having, if we scroll back a little bit, where we ended up having a standard linear algebra problem, where we have a matrix A which multiplies with the unknown vector, and that is given by a known vector on the right-hand side. Now, since this is a tridiagonal matrix, to invert the matrix A is very inefficient. And there is a famous algorithm for solving this type of problems, which is called Thomas algorithm. And this is a very efficient way of solving this type of problems. And when we compare the results with 10 integration points, then the neural network was actually far superior, with an error which was close to what you see here, whereas the standard numerical scheme had an error on the order of 10 to the minus 3. Now, in increasing to 100 points, we get something which gives a better result with the standard numerical scheme. But just keep in mind, as we also said before the break, is that when we increase the dimensionality of these type of problems, if we were looking at a three-dimensional problem, or we have more complicated problems where we actually need to have many more integration points, then a neural network can actually be competitive compared with the standard methods. And you will often encounter differential equations of the higher order type, which are often solved by neural networks, because they can often lead to approximations to the solutions, which are more feasible from a computational point of view than the standard numerical methods. You will actually see that if we were to increase this problem here to 2 dimensions, then the standard differential approach, the differential equation approach to this type of problem becomes quite more convoluted. It's still easily to do, but it becomes more complicated. So when we're dealing with partial differential equations, what we then have is a similar setup, but now we have more variables. So it means that our function g does not depend only on x, but it can depend on variables x1 up to an xn, and it has derivatives in terms of these different variables. It has higher order derivatives, etc., etc. So a differential equation which we are going to look at is the standard diffusion equation in the example below here. This means also that we are going to repeat much of the same machinery, except that now we will have a trial function which has to depend on the different variables we have. So in the example below, we are going to look at the diffusion equation in 1 dimension, which means that we would have x and then time in addition. So the role of these functions is to ensure that the output is 0 when this gt is evaluated at the values x1 and xn, where the given conditions have to be satisfied. It doesn't need to be 0, but this could be a case when we are looking at boundary conditions where we have put the boundaries to be 0, like in our previous case. But these boundaries do not need to be equal to 0. They could take some other value. So the network then will then, the way we are going to calculate it is actually to repeat the same time of machinery, except that now we have more variables. So this is essentially the difference from the previous cases. And the cost function is again going to be given by this difference between the left-hand side and the right-hand side squared. But now this has to be a function of all the different variables which we have. And we have to now look at the both x1s, x2s, etc., etc. So keep in mind that in the previous case, when we had a 1-dimensional problem, then we had only 1 input node. Now we have 2 dimensions. As you can see from the diffusion equation here, we have x and time. So position and time. That means that we are going to need 2 input nodes, 1 for x, since we're in 1 dimension, and 1 for time. And each x and t are going to output a specific value for the function g. So the output is still going to be given by 1 value. And then we can run this for many integration points here. So we can have 100 integration points for x and 100 integration points for t. So that means that we will have 100 plus 100. So we would have 200 input variables, but we will still only have 2 nodes. So each node would then have 100 input variables if we have 100 values for x and 100 value for t. So this is what would change in the setup of a neural network, and that is the set of input nodes which are needed. So this is a typical problem which we could have. So we have g of x at time t equals 0 is given by some known function. And then we could say that the boundary conditions are so, and these are the standard von Neumann boundary conditions. And these are the Dirichlet boundary conditions. And this means that we put the values that the function that this boundary points to a constant. In our case, we just simplify that to put it equal to 0. So x is defined between 0 and 1, and t is simply larger or equal to 0. And t equal to 0 is our initial time, as you can see here. So this would be the equations, and we can solve this by standard implicit schemes or explicit schemes and many other different types of schemes. And that's what we will compare that with below here. When we are setting up the neural network now, as I said, the only difference between the previous cases is that we are going to have a slightly more complicated function here. And we need also to take care of the fact that we have 2 input nodes, one for time and one for x. So this will be the pairs of inputs. And when we now are setting up, so here I'm just setting up the network. And now we have to be a little bit more careful when we are setting up the trial function, which we want to start with. So again, we are going to have a function which runs like this. So the function now is going to have a part here, which we looked at earlier, which is given by x times 1 minus x here, which ensures that we get the boundary conditions. And then this is multiplied with time, as you can see here. And the function h1 here is a function which we want to obey the boundary conditions, the initial conditions. So we are now defining the initial conditions in terms of a sine pi of x multiplied with 1 minus t here. So this is going to be my trial wave function, which now respects the initial conditions. So these are the results when t equal to 0. So the function which I want to set up now is now given in terms of this h1 times this function here, which multiplies with the neural network and which ensures that the boundary condition is also fulfilled. So we need now to set up a Jacobian because we have a second derivative which will depend on both x1 and x2, or x and time. So we need a second derivative in terms of time if you look at the differential equation, we have a second derivative in terms of x and a first derivative in terms of time. So setting it up then, let's just run this. And then we are going now to have an analytical solution for the problem which we are setting up, which is simply given by the exponential of minus pi squared times t times sine pi here. So let's see what our network is actually going to give us. So you will see that the initial cost is pretty high. And in this specific case, with a simple neural network with just one layer, we may actually not get the very best results. We are going to skip the next example. This is going to take a little bit more time because now we have 2 input nodes and we have time and position as possible variables. So typically this is going to be a more time-consuming operation. And it normally takes a little bit more time here. So which gives us time for making questions. So guys, I mean, if you have questions you would like to make, I mean, don't hesitate. And also if this is a type of problem which you would like to study further, I will make a path for the second project, which deals with the solution of differential equations, if this is something of interest. But you see easily now that this becomes more time-consuming as we increase the dimensionality of the problem. So maybe we can just leave this one and just move to the next topic while this is running here. It takes normally a little bit more time than what you saw for the one-dimensional cases. So the next topic, which I wanted to start with now, is the discussion of convolutional neural networks. So this is going to be our next deep learning method. And let's now bring up the Jupyter Notebook for convolutional neural networks. So let me just bring that up. Maybe that should be here. Here we are. So the topic which we will discuss in more detail from now on is about two very popular deep learning methods. And one of them is convolutional neural networks, and the other one is recurrent neural networks. Convolutional neural networks are perhaps the type of neural networks or deep learning methods which have achieved perhaps the highest level of popularity, because this is a standard approach for image recognition. So if you're thinking of everything from recognizing images to facial recognitions and so on, then convolutional neural networks are actually the type of neural networks which are widely used for that type of tasks, for image compression, etc., etc. So I put up some videos if you want to look further. So there are videos on deep learning methods. There are videos on convolutional neural networks from MIT. There's another one from Stanford, which actually taken from lectures on deep learning methods from these two universities. There are also some lecture notes from Michael Nielsen, who actually wrote one of the more popular books on quantum computing back some 20 plus years ago. So why do we do convolutional neural networks? Now, one of the reasons for doing this is that we are going to use the mathematical process or operation of convolution. And I assume that you may have heard of that before. And the mathematical process of convolution is at the center of convolutional neural networks. And what is typically done is that we are decreasing the dimensionality of an image by gradual filtering down the dimensionality. And the filtering is done by the mathematical operation of convolution. So I will try to explain to you what that means, and then we are going to look at specific examples. If you look at the so-called MNIST data, which we discussed a little bit earlier, that is a data set which actually has been scaled down from images which had 28 times 28 pixels to images which have 8 times 8 pixels. And when we had 8 times 8 pixels, we ended up with 64 input nodes. A typical image has perhaps 200 times 200 pixels, or even more. And it has typically 3 color channels, which are labeled as R, G, and B. And these color channels give an additional dimensionality. So if you have a color image of 200 times 200 pixels, you would have in addition the 3 color labels R, G, and B, which then gives an image of dimensionality 200 times 200 times 3. So these would be the number of input nodes which you would need. And if you then look at a standard neural network, that means that the number of input nodes would be 200 times 200, which is 40,000, times 3, which again would give you 120,000 input nodes. And these 120 input nodes would then be connected to different hidden layers. So if you now look at the dimensionality of a neural network, if you take as an example an image of 32 times 32 times 3 color channels, then you would need something, if you have a single fully connected neuron in the first hidden layer, just one single fully connected neuron, that will give you 3,072 weights to define. And if you add that, if you had more than one hidden neuron in the first layer, suppose you have 100, that will give you 3,072 times 100 weights to determine. So clearly, this type of affine transformations, that means full matrix times matrix multiplications and matrix times vector multiplications, which we did in a standard neural network, is something which, for these large images, becomes simply unfeasible. So you could even say that if you have an image of a more respectable size, which is a 200 times 200 times 3, that would lead to 120,000 weights just for one single neuron. And if you then have 100 neurons, you would then have 12 million weights to determine. And if you move on, then you can quickly see that this type of transformations or operations, which we did with a standard neural network, would typically become overwhelmingly expensive from a numerical point of view. And that's why we would need some kind of dimensionality reductions. So as you can see from the text here, you can now view a CNN as an efficient way to reduce the dimensionality of an image. So that means that we would actually, through different filters, we are then going to scale down the images to a smaller dimensionality. So a typical neural network of the convolutional type is now given by a set of different types of filter operations. So you can then think of it in the following way. If we now switch back to the whiteboard, so let's do that. So if you look at the CNN, the way you can think of it is now that you have an image, and suppose now it looks like this, and this image, so I'm setting it up in with the color channels. So you could think of an image which is a 32 times 32, and then it has 3 color channels. What could happen then is that we take a filter, which is a 5 by 5 times 3 filter, and this squeezes down the image to a smaller dimensionality, and we are coming back to this. And I would then produce this many times, so I could now produce more such images which have been reduced in dimensionality. And this will now continue till we have flattened down the image to a smaller dimensionality. So if you're thinking of a typical example of a house, the house, when you want to scale it down, you would typically not include all the images or all the pixels which you have, because the house would have, let's say, a painting, and that painting would give a uniform type of information from the walls. And the only thing you would like to keep then as information would be the corners of the house, where the windows are, where the doors are, where the roof is. So when you're scaling it down, you don't need to include all the information about the paintings of the wall, if we assume that that painting is pretty uniform. So if you have 200 times 200 times 3 for a photograph of a house, when you want to filter it down and recognize this as a house later and train models so that you can actually recognize houses, you don't need to include the information about the painting for all the parts of the wall. So that means that you would actually filter out the information which is most important. And the typical convolutional neural network consists of stages where you have an input here. So this is your input layer. And then you bring this into what is normally called the convolution stage. And that convolution stage contains several types of operations, which we are going to discuss a little bit more in detail. So one part here is the mathematical process of convolution itself. And that means that we are scaling down the image. So I'm writing convolution here, but you can read this as a filter, where you actually reduce the dimensionality of the image. Then when you have filtered it down, there is something which now includes a operation, a mathematical operation, where you're reducing further dimensionality. And then you would have an activation function here of the typical ReLO type. Then there is a further scaling down, and this process is called pooling. And we are going to discuss that a little bit more in detail, what that means. But a pooling function replaces the output of the net at a certain location within what's normally called a summary statistics. And that summary statistics can be that you now look at the specific nodes which you're left with, and you would keep only for the nearby nodes, you can just pick sets of nearby nodes and then just spit out the largest value. We are going to look in more detail into that. Now, in principle then, what you could do is to perform a new convolution here. So I'm just going to put that with dots here. So new conv stage. So this is often repeated many times. So that means that you're filtering down the image to smaller and smaller dimensionalities. And then at the end, what you have then is the final stage, where you now have flattened out the data. And this is normally a standard neural network stage. So that means that you have reduced the dimensionality of the image to something which is tractable by a standard neural network. And when you're in that stage, then you would typically run the standard neural network calculations, set up the different cost functions which for that specific stage which you want to deal with. And then you would simply train the parameters by the standard backpropagation. So in the NN stage, this is now where you would produce the final output. And then you would compare that with the data which you want to train against. So, or the target values. So that output is then fed into a cost function, which you then use to determine whether what your network is producing is acceptable or not. And this clearly goes back and forth. So you would then, when you perform the first stage here, you would then typically go back again, and then you can do new filterings, etc., etc. So in the convolutional stage, there will be parameters you need to train. In the ReLO stage, there will be no parameters to train, and the same in the pooling stage. But then in this stage here, you would then have parameters to be trained by the backpropagation algorithm. So the backpropagation algorithm is at the heart of basically everything which you're doing. However, there will be stages here where you don't have any parameters you're going to train. And we are going to look in more details into that also next week. But now I just wanted to set up some of the basic overarching items which define a convolution neural network. And if you want to have the kind of essential message, is that you can view a CNN as a way to effectively reduce the dimensionality of an image, where you train the network to specific properties of the image. So keep in mind now that this training and the type of filters you apply are often very specific to the type of problem you're looking at. So if you're training against houses, buildings, etc., there would be specific filters which you would apply. So if you're training against houses, you would keep information about the corners, windows, doors, the roof, etc. And you may be less interested in keeping all the information about the colors on the walls. Similarly, if you're training against other types of buildings or bridges or whatever, you have some type of information you're going to keep. And that means that the filters will be highly fine-tuned to the type of problem you're dealing with. If you are dealing with humans, you may keep information about the eyes, the mouth, the nose, etc. But you may not be interested in fully in the way this human is actually dressing, etc., etc. So the many of these big networks which have been trained by using millions and millions of images, they often fine-tuned to the specific type of problem. So convolutional neural networks have also been used and are used for type of regression problems, but their wide popularity stems very much from applications to image recognition. And to image recognition, this is perhaps one of the really, how to say, impressive applications of deep learning methods. For us doing nuclear physics, this is also quite interesting because often we have images from scans. Some of you will do medical physics and you will have scans of tumors from patients and you would like to recognize these tumors. If you are looking at the output from a detector, from a numeric or from a specific experiment, you may have charged particles which move in a magnetic field and they make a specific path in the detector. And then you can, from the images resulting from the detector, you can actually recognize whether that could be a proton, or it could be another charged ion, or whatever you're looking after. So CNNs have also been widely used in detector recognition, in the recognition of specific events in experiments. So it is a field which is a field of deep learning, a method of deep learning which is widely used in tons of different types of applications. Any questions so far before we move back to the Jupyter Notebook? So this was more meant to give you a kind of overview of the basics of convolutional neural networks. So think of this as a way to reduce the dimensionality of the problem. So typically, the convolutional neural networks take advantage of the fact that the input consists of images and they constrain the architecture in a more sensible way. So if you now look at a typical neural network, which is now run through a CNN, so you would have a typical input layer that holds the raw pixel values of the image. And then there is a convolutional layer, which will compute the output of neurons that are connected to local regions in the input, and each computing a dot product between their weights and a small region. So this is the filtering itself. And then there's a ReLU layer, which apply an element-wise activation function. And then there is a so-called pooling layer, which performs a further downsampling. And we are going to look at the specific details here pretty soon. And then there's a fully connected layer here, which could then be typically a standard neural network. And in that specific case, you would simply run through the whole training there. So in brief, we have a few distinct types of layers. There's a convolutional, there's a fully connected layer, there's a ReLU layer, and there's a pooling layer. These are by far the most popular ways of doing that. And I also recommend to take a look at the textbook by Goodfellow, because that contains an in-depth discussion of many of the basic properties of convolutional neural layers. So the key idea is a mathematical operation, which is represented by convolution. So I wanted to give you some basic mathematics first, before we start looking at the details. And if you scroll down here for the topic next week, we are actually going to look at how we can set up a convolutional neural network code. But you could now think of you running an experiment where you register the position of an object, and that position of the object may have some noise. And what you want to do now is to filter away some of the noise. So you could now think of a continuous function, y of t, which is given by the position which we measure at a given time a, just to give you an example. But then this is filtered away because these results may be noisy. So you could think of this w as a way to filter away the noise in your measurement. And what you see here is simply the mathematical definition of convolution. So you would typically then write this in a more compact form, like this y of t with x with this asterisk with w, which simply represents the convolutional process, which is actually given by this function here, which is called a weight function, times this x, which could represent the measurement which we are doing. And then you end up with the value which you see here. So you could now think of having devised a specific filter which takes away your noise. Now, the discretized version is simply something which runs from a equal minus infinity to plus infinity. But often you would actually limit these sums here. Now, so one of the things which we are going to do now is actually to look at some simple examples of what this actually means. And sometimes these gives us simpler ways of actually determining the final output here. And the inverse of that process, which is also well defined in terms of another integral, is then normally called a deconvolution here. So let's now look at a specific example which you may be familiar with. So this example here is actually given by a polynomial of order 2 here, and I have another polynomial of order 3. So here we can actually use the mathematical process of convolution to look at the polynomial multiplication. So, and that is actually more efficient than us writing out p multiplied with s. So if you think of a polynomial multiplication here, what you should end up with is a polynomial of degree 5, because this is a polynomial of degree 3, and this is a polynomial of degree 2. So that means that we should get something which looks like this. So there will be a 0th order, a 1st order, 2nd, 3rd, 4th, and 5th order. And if we now compute the products, we know that this is something which can be, oops, here there's a typo. So it should be alpha 1 times beta 0 and alpha 0 times beta 1. So this is actually, there's a small error here. I see that one now. Okay, but this delta 0 would simply now be the alpha 0 times beta 0. I know that delta 1 looks like this. Delta 2 is now alpha 0 times beta 2. So these are the 2nd order terms, the 3rd order terms. And we know easily, we see easily from the above equations that delta 5 simply has to be equal to alpha 2 times beta 3. So we know now that alpha y is 0, except for these 3 values. And beta 0 is actually 0, except for these 3 values here. Okay? Any questions so far? So that means that we can rewrite the coefficients delta I using a discrete convolution. And it's easy to see that this is actually what applies. Or we can write it as a double sum with a specific restriction. Now, in our specific case, this can actually be reduced to specific sums from I equals 0 up to I equal to 3, because these are the only values which will take place. So we would actually write this parameters delta in terms of this convolution operation here. So this is one of the simplest cases of convolution applied to polynomial multiplication. I don't know if you've seen this example before, but this is just meant more to guide the eye to what is going to come here. So if you look at this process here, the way you can actually do this now is to, since we only have a finite number of alpha and beta values, which are non-zero, we can actually rewrite these operations here as a matrix times a vector. Now, the process is commutative, the process of convolution. And you can see that you can actually rewrite the multiplication in terms of a matrix holding beta and a vector holding alpha. And in that case, you would actually rewrite it in terms of this matrix multiplied with this vector here. So when you're implementing the above equations, we do not encode and allocate memory for the matrices explicitly. We rather code the convolutions in the minimal memory footprint that they require. So in a certain sense, you would never rewrite this as a matrix times a vector, because that means that you would actually have to store these quantities. And what you would rather do then is actually to rewrite this one using the smallest amount of memory which is needed. So the other thing which is interesting to note is actually that this operation here, that is an operation which when you rewrite it in terms of a matrix holding beta, this actually gives less floating point operations than the previous one. So these matrices are normally called Topliss matrices. And the process of convolution, the reason why I'm bringing this up is that mathematically, the way convolution is implemented in convolution neural networks is actually through these so-called matrices, these Topliss matrices. So these Topliss matrices, that's a matrix in which each descending diagonal from left to right is constant. So you can actually, you see now that in this case, this line contains constants, this line contains constants, same here and same here. And so that means that you could, for instance, the last matrix is something which you could rewrite like this. And the elements are normally defined simply by this AII equal to AI plus 1 and J plus 1. And this is normally rewritten as AI minus J. These matrices do not need to be square matrices. And Topliss matrices are also closely connected with Fourier series, which I have an example of here, which is another case of convolutional. And what this example shows is that we can represent linear convolution as a multiplication of a Topliss matrix by a vector. And this is one of the ways normally convolutional neural networks are implemented in different codes. So when we are implementing these filters, you can then think of these as being represented by specific matrices, which are normally given by these Topliss matrices. And we're going to see an example below here. So before we move on, I just wanted to say, I'm just skipping these terms on Fourier transform, which is just an example. So basically, the way you can think of these processes is now to implement a filter, which is defined by normally what's called a kernel, K, which then leads to an output S. So you would have an input image here, and then you have this filter, which is normally called a kernel. And the way we would represent this, if we now have an image in 2 dimensions with just one color channel, then we would represent this filtering through this operation here. And as we will see next time, we are going to rewrite this in terms of these Topliss matrices. So I'm going to stop here today, because this is what we have gone through now represents some of the basic mathematical operations. And I invite you to take a quick look at the examples which we're going to look at. So the example which you see here contains now a input matrix, which is a 3 by 3 matrix, and it has a filter which is of dimensionality 2 times 2. And this operation here is something which I can rewrite in terms of a Topliss matrix multiplied with a vector. So the filtering here is going to give us a reduced image. And the technicalities behind that and how we can implement it is something which we will discuss next week. But I take the liberty now of just mentioning this. And if you have time, please take a look at the material which is below here. And I also recommend, if we now scroll back again, to take a look at chapter 9 in the textbook by Goodfellow et al. Here. So this is actually up here. So this textbook is a deep learning textbook, but then you also have a nice implementation of CNNs in Aurélien Géron's book in chapter 13.